Just think about your day for a second. Your phone, right? Your laptop, maybe you drove an EV today.
Or even just the power from the wall, increasingly from solar and wind.
Exactly. And the common thread running through all of that, it's batteries. They're not just add-ons anymore. They feel absolutely fundamental, like the bedrock tech for the energy future we're all talking about.
Foundational is the right word.
So today, yeah, we're doing a deep dive into what's happening right at the cutting edge of battery innovation. And it feels like things are moving incredibly fast in this space.
Oh, absolutely. And to help us navigate, we've got this really comprehensive document, Advances in Battery Innovation. It kind of lays out the whole picture. New chemistry, sure, but also manufacturing, safety, how long they last, the whole life cycle.
Right, and our goal here for this deep dive is really to cut through the hype and figure out what the most important changes are right now. The stuff that's actually making decarbonization happen, or making EVs practical for millions, or letting us really use renewables properly.
Yeah, we want to unpack what's changing, why it actually matters for you listening, especially if you follow this field and where things seem to be going.
Okay, so let's start with why. Why this sudden, explosion in battery innovation?
Well, the source points to some really big drivers, urgent ones. We've got the massive push for decarbonization globally.
Can't avoid that one.
Nope. Then there's electrifying transport cars, trucks, buses, the whole lot. And maybe the trickiest bit, integrating renewables. Solar and wind, they aren't always on when you need the power.
So you need storage. Lots of it.
Exactly. And the document makes it clear this isn't just about lithium ion getting 5% better each year.
No, it feels like the whole playing field has just gotten way bigger. More options popping up.
That's it. We're really moving beyond just tweaking lithium ion. The source talks about some exciting new contenders, solid-state batteries, for example.
Ah, yes, the holy grail everyone talks about.
Yeah.
Why is that?
Well, the big promise is safety, mainly because they use a solid electrolyte instead of a flammable liquid one. But they also hold out the potential for much higher energy density, more power in the same space, basically.
Okay. And then you mentioned sodium ion. What's the story there?
Abundance. Sodium is just everywhere, dirt cheap compared to lithium.
Right. So maybe not for a high-performance EV, but...
Exactly. The document suggests it's really promising for things like grid storage or maybe lower-cost vehicles where absolute top-tier energy density isn't the only factor. And there are others mentioned too, like lithium sulfur, metal air, lots of research happening.
So it's not just about packing more punch, it's a whole range of goals.
Totally. Yes, everyone wants better specific energy, more power for the weight and volumetric density, more power for the size. But it's also about cycle life. How many times can you charge and discharge it before it wears out? And safety, always safety. Plus, trying to use materials that are easier to get, avoiding those supply chain bottlenecks or ethical concerns with some metals.
Okay, let's pivot a bit, because the source makes a really interesting point. It's not just the chemistry inside changing, but how we actually make these things. The manufacturing side is also seeing huge shifts.
Yeah, that's crucial. Manufacturing has often been the slow, expensive part. Lots of energy, nasty solvents.
Like that NMP stuff.
Exactly. NMP, N-methyl-2-pyrrolidone. Standard solvent, but requires careful handling and recovery, adds cost and energy use. So the document highlights things like dry electrode processing.
Dry processing. Sounds simple, but I gather it's a big deal.
It really is. Getting rid of those solvents, especially NMP, cuts energy use way down, simplifies the production line, reduces costs. It's one of those enabling technologies you need to really scale up production sustainably to the gigawatt-hour GWH levels we need. It's almost a paradigm shift.
And roll-to-roll manufacturing makes me picture like printing newspapers.
It's a good analogy. Continuous coding, processing, much faster, much more consistent than making things in batches. Higher throughput.
And 3D printing batteries.
Yeah.
That sounds futuristic.
Well, it's happening. Additive manufacturing lets you create really complex battery shapes. Think tiny batteries for micro devices, or flexible ones, or ones integrated into weird shapes, like in medical implants, perhaps. Stuff you just couldn't do with traditional methods.
Wow. Okay, but if you're making them faster and maybe more complex, how do you make sure they're actually good and safe?
Quality control, yeah.
Got right.
That's where automation and what the source calls inline metrology come in. Basically, sensors and systems checking things like electrode thickness, composition, looking for defects while the battery is being made, real-time checks.
Instead of just testing at the end.
Right. It's essential for catching problems early, ensuring consistency, and ultimately safety, especially when you're turning out millions of cells.
So for you listening, these manufacturing changes aren't just factory details. They're what could make advanced batteries affordable and available at the scale we need. It's how the lab ideas get into your car or onto the grid.
Precisely. Okay, now let's dig into the core, the actual materials inside, the electrochemical bits. The source really emphasizes that performance is all tied up in the specific materials you choose for the cathode, the anode, the electrolyte.
This is where the chemistry really gets intense, right?
Right.
What are some key examples from the document?
Okay, so for lithium-ion, the familiar stuff, it mentions common cathodes like NCA, that's lithium, nickel, cobalt, aluminum oxide, or LFP, lithium iron phosphate, and anodes like graphite, the standard. But it also calls out silicon as a really interesting next-gen anode material.
Silicon. Why is that getting so much attention?
Huge potential energy density. Theoretically, silicon can hold way more lithium ions than graphite, like 10 times more, potentially.
Wow, so what's the catch?
It swells up a lot. When it absorbs lithium, it expands massively, and that repeated swelling and shrinking basically pulverizes the electrode over time, killing the battery life.
So the trick is managing that swelling.
Exactly. Researchers are doing clever things with nanostructures, mixing silicon with other materials, creating composites, trying to give it room to breathe, essentially.
Okay, and for sodium ion, different materials needed there.
Yeah, because sodium ions are bigger than lithium ions, so you need structures that can accommodate them. The source mentions things like layered oxides for the cathode and hard carbon for the anode materials specifically chosen for sodium chemistry.
Makes sense. And solid state. The electrolyte is the key material there.
Pretty much. Finding solid materials, ceramics, sulfides, polymers that conduct ions well and are stable and can be manufactured, that's the challenge. But if you crack it, you get that safety and energy density benefit.
And for the really big grid batteries, you mentioned flow batteries.
Right, redox flow batteries. Totally different concept. Energy is stored in liquids in big tanks. The source mentions common ones using vanadium ions dissolved in acid, or newer types using organic molecules. You scale up the energy just by making the tanks bigger, great for grid scale.
So across the board, materials innovation is about speeding things up, making them last longer, holding more energy.
All the above. Yeah, increasing how fast ions can move in and out, that's intercalation kinetics, improving stability, especially against heat, pushing the voltage higher to get more energy per cell. And a really big push now is sustainability, finding abundant, eco-friendly materials, designing out cobalt or other critical metals where possible.
Let's talk lifespan then, because batteries don't last forever. The source dives into life cycle and durability.
Right, two key ideas here, cycle life and calendar life. Cycle life is kind of what you expect. How many charge-discharge cycles can it handle before the capacity drops too much? Often they use an 80% capacity retention figure as the benchmark.
Okay, pretty straightforward, but calendar life is different.
Yeah, that's how long it lasts, just sitting there. Even if you're not using it much, it degrades over time anyway.
Why? What's happening inside?
Slow, unwanted chemical reactions. Things like the SEI layer, the solid electrolyte interface, continuing to grow slowly on the anode, consuming lithium. Or the electrolyte itself slowly decomposing. These things happen constantly, gradually reducing capacity and increasing resistance. It's a major focus for improving long-term durability.
Okay, now this is where it gets really interesting from like a circular economy perspective. What happens when a battery is done? Say an EV battery that can't quite power the car anymore.
Yeah, it's usually not totally dead. That's where second life applications come in. A battery might only have, say, 70-80% of its original capacity left. Not ideal for a demanding car, but perfectly fine for stationary storage.
Like in a house backing up solar panels.
Exactly. Or for businesses managing peak demand. It gives the battery a whole second career, extending its value and delaying recycling.
But eventually it does reach the end. But then, end-of-life management.
Right, and this is getting way more sophisticated. The source mentions innovations in recycling. There's direct recycling, which tries to refurbish the valuable cathode materials directly without breaking them down completely.
Keeping the structure intact.
Ideally, yeah. Saves energy and materials. Then there are hydrometallurgical processes using liquids and chemical reactions to dissolve the battery materials and selectively recover valuable metals like lithium, cobalt, nickel. The goal is closing the loop, getting those materials back into new batteries.
Reducing mining, reducing waste. Makes sense.
And the source emphasizes managing this whole lifespan from design to second life to recycling needs a systems approach. You have to think about it all from the beginning.
Definitely. Okay, we absolutely have to talk about safety. It's always the elephant in the room with powerful batteries, isn't it? The source tackles this head on.
As it should. Especially as energy densities climb higher, managing safety risks is critical. The big one everyone worries about is thermal runaway.
That's the fire risk, where it just keeps getting hotter.
Exactly, a cascading failure. So the document outlines mitigation strategies. We already mentioned solid-state electrolytes being inherently safer because they're not flammable.
Right. What else?
Adding flame-retardant chemicals to liquid electrolytes, designing cells and packs to better contain or vent heat if something does go wrong, better thermal management systems.
And protection against, like, physical damage.
Right.
Or electrical faults.
Yep, that's covered too. Mechanical protection, robust casings, internal structures to prevent short circuits if the battery is crushed or punctured, and electrical protection, things like fuses, circuit breakers, current interrupt devices, sophisticated monitoring to detect overcharging, over-discharging, short circuits.
Which brings us to the battery management system, the BMS, the brain.
The indispensable brain. Advanced BMS algorithms are key. They're constantly watching voltage, current, temperature, even impedance, cell by cell. They use this data to keep everything within safe limits, balance the cells, and crucially, detect early warning signs of trouble.
So it can shut things down before it becomes a major problem.
That's the goal. And the source also points out the importance of rigorous testing standards, UL standards, IEC standards, UN transport standards. These ensure batteries meet specific safety requirements before they can even be sold or shipped.
Okay, that's reassuring. Let's maybe peel back one final layer. The fundamental science. How does this stuff actually work? The source touches on the core electrochemistry.
At its heart, it's pretty elegant, actually. All rechargeable batteries rely on reversible redox reactions, reduction and oxidation.
Okay, redox. Break that down.
So during discharge, when you're using the battery, at the anode, you have oxidation. The anode material loses electrons. A classic example is lithium metal giving up an electron to become a lithium ion, Li-O plus E.
And those electrons are the electricity we use.
Exactly. They flow out through the external circuit, powering your device. Meanwhile, at the cathode, you have reduction. The cathode material gains electrons. For example, cobalt ions in the cathode might gain an electron, like Co-U plus eco.
And what about the ions, the Li-U?
They travel through the electrolyte, the internal pathway from the anode to the cathode to keep the charge balanced. When you recharge, the whole process runs in reverse. Electrons are pushed back by the charger, ions travel back through the electrolyte.
Okay, got it. Why is understanding that fundamental process so important for making better batteries?
Because everything hinges on how well those reactions happen. The voltage the battery provides is determined by the energy difference between the anode and cathode reactions. How fast you can charge or discharge depends on how quickly electrons can transfer and ions can move.
Ah, the rate capability.
Right. And efficiency losses often come from resistance to ion movement or side reactions. The source specifically mentions things like understanding how that SEI layer forms and evolves, or how the electrolyte breaks down over time. These aren't just minor details, they are fundamental electrochemical processes that limit battery life and performance. Nailing the fundamentals is key to the next big leap.
Okay, so zooming back out, looking ahead. The source provides a strategic outlook. What does the future look like? It sounds like a mix of many different approaches.
It really does. The document paints a picture of convergence advances in materials science, coupled with more sustainable manufacturing, and this idea of a circular economy where we reuse and recycle everything.
What are some of the really cutting-edge directions mentioned?
Well, beyond the chemistries we've talked about, they point towards potentially even further out stuff. Using ions that carry more charge, like magnesium or zinc, multivalent ions, exploring really high concept ideas like lithium-air batteries.
Lithium-air, that sounds intense.
Very high theoretical energy density, also things called anion redox systems, pushing the boundaries of electrochemistry itself.
And solid state comes up again with some pretty wild claims.
Yeah, the potential for ultra-high energy densities, maybe enabling things like electric flight eventually, and even sub-second charging times. Imagine plugging in your phone or laptop and it's full in literally a second.
Okay, that would change everything. And green manufacturing seems like a core theme for the future, too.
Definitely. The source stresses moving towards low-emission processes, using water-based methods instead of harsh solvents, designing for disassembly and recycling right from the start. Sustainability has to be built in.
and batteries playing a smarter role in the grid.
Yeah, grid-integrated systems, batteries won't just be dumb storage boxes. They'll actively help manage the grid, smoothing out demand, providing frequency regulation, becoming much more dynamic assets. And finally, the source highlights policy and standards.
Ah, the less glamorous but essential part.
Crucial. Getting global agreement on safety rules, performance benchmarks, recycling protocols, that's what allows these technologies to scale up safely and be adopted worldwide. You need common rules of the road.
So wrapping up this deep dive, it's clear the battery world is just buzzing with activity. It's incredibly dynamic.
Absolutely. It's pulling together chemists, materials scientists, engineers, mechanical, electrical, chemical, even data scientists building smarter BMS systems. It's truly interdisciplinary.
And the breakthroughs are happening everywhere. New materials, smarter ways to make them, better safety, longer life, and thinking about the end of life right from the start.
Yeah, all these innovations together are really paving the way for the kind of powerful, affordable, and scalable energy storage we absolutely need for the future of, well, pretty much everything, transport, industry, the grid.
Okay, so final thought for you, the listener. We've covered a huge amount of ground, from the tiniest atoms doing their chemical dance inside the battery, all the way up to global manufacturing trends and policy. Given all that complexity and the rapid pace of change, what area do you think will be the single biggest hurdle we still need to overcome? Or, put another way, what single breakthrough do you think will be the most transformative to truly unlock the future powered by these advanced batteries? Something to chew on.